Okay, thank you so much for coming early this morning for the second part of topology. Again, the story is obviously that topology is really, really beautiful. So if you don't enjoy it, please come to me, complain. It's all my fault. Yeah, so let me pull up what we did yesterday, last time. So Monday, not yesterday. So essentially, we have this idea of having a certain type of one-dimensional object that we call a graph. You see on the right-hand side here. And it has kind of little vertices, like blown up points, and the edges between them, which is like the connectivity. And what I always want to think about is that there's some real-world situation, whatever it is, streets, whatever, and you want to model it using a graph, right? So here's some real network, and on the right-hand side is our graph representation. So that's what you do all the time in mathematics. You take some real-world problem, turn it into like a toy problem, a toy model of the real-world problem, and then kind of stripe the real-world as the toy problem away from any applications that you can see, just to have you're rocking in a little bubble, essentially, and you're trying to say as much as you can about the object itself, kind of forgetting this side, because eventually people will come from here with very, very different problems, and you want them to just grab your ideas, your results, and just pull them over to their situation. That's what mathematics does all the time. So mathematics usually lives in some little bubble, some little toy model of the world, which makes it so nice, because in our toy model, kind of everything is a little bit nicer and a little bit easier, and we can write down kind of formal theorems, formal statements that others can then just grab and apply in their situation. So what we're trying to do in this first part of the lecture, we're looking at these type of objects, always keeping in mind that they come from something in the real world. You could think of train tracks or whatever. And we try to say as much as we can about them in some abstract framework. Right? You never know what kind of real world problem will come up in the wild. So you want to be prepared and have as much kind of abstract properties as possible. And then there's this other part of doing mathematics, which is you just enjoy your toy model. You can forget about the real world altogether, and you just enjoy being a mathematician and play around with those little pictures. And just to convince you, so this is not just me trying to motivate things. So people really do this in the real world. So if you, this is really the train, the main train tracks of the United States. It's exactly what you think it is. It's a bit more dense along the coast and a little bit sparser in the middle. But as you can see, it's a graph, right? So it's kind of a graph. It's a decorated graph if you want. You might want to put some decorations on your graph eventually, and we will do the same as well, right? So keeping track of that the train track between Los Angeles and San Diego is a little bit more popular than the one between Denver and Salt Lake City. But it's a real-world problem. It's really just a graph, and I would like you always to keep that in mind. And it's just really absolutely fantastic. So I stole this one from a biology book. So people really take the brain and model various things in the brain using graphs. As you can see in this setting, and we will do that maybe today, maybe tomorrow. As you will see, maybe it matters for those applications to kind of keep some geometry, some properties, how the graph arranges in space into account, and we will do that as well. Right? So we want a little kind of setting of properties where people just can grab the properties and apply them to their real-world situations. I think that's actually pretty cool. Here is one last one for you. So the Facebook, or people nowadays, so this is the real one. Oh, this is a really bad picture. Give me a second. So you could think of any social media. Just you are some user, and maybe your friends are the ones that are connected via edges, and then people study social media via graphs. So it's really fantastic. It's absolutely amazing. So I say it again, what we really want is to kind of cook up a setting such that people can grab various ideas that we kind of present in a kind of our little bubble here. Okay, So what we did last time is I kind of had this notion of a graph, and there were two different notions essentially. I had the one that is just given by I have some vertices and have some edges, which is exactly what a graph should be. You have the people on Facebook, and the edges are the connections. There's nothing else associated to the graph. But as you if you have seen this picture of the brain, we have seen that before, somehow it also matters how the graph looks like. So I really want to draw it instead of thinking of it as an abstract object. And here's a drawing of this graph, and I remind you how that works. I just put my 1, 2, 3, I just put them 1, 2, 3, right? My little vertices are just whatever they are. And the edges tell me how things are connected. So there are 3 loops. Well, 1, 2, 3. And then there's an edge from 2 to 3. And recall that in this setting of the oriented one, the first one is where it starts, and the second one is where it ends. So I draw a graph, I draw an edge from 2 to 3. And at the bottom, for example, you have an edge AB and an edge BA, and they go in opposite directions. So our goal is to kind of study more properties of these objects, always keeping in mind that what we're really doing in topology, we're really interested in them as intrinsic objects. They somewhat live nowhere, but eventually we maybe want to kind of draw them because it's kind of nicer to have a good picture in mind. And we'll play around with those ideas for essentially the rest of this week and for probably half of next week anyway. So whenever let's continue. So let's start with today's lecture after the introduction part. So whenever you're studying some properties in mathematics, you have some form of structure you're studying. You're studying a vector space or something like this. It's always a good idea to have a notion of what is a substructure of your structure. And in our case, it's what is called a subgraph. Right? What is a subgraph? Maybe I just pull it up. So a subgraph is, well, there's a subset of the vertices and there's a subset of the edges. Okay? So let's do the example here. So this is my parent graph, G, and this is my subgraph, H. And all I'm saying is I'm taking out a certain number of vertices, I pick them, and I put some edges between them, and whatever comes out is a subgraph of my original graph, right? It lives in my original graph. And the way we do this is we just say abstractly, okay, my subgraph is just really just subsets. So there's a set W and there's a set F. F is a subset of E, some sub-edges like those guys here, and W is a subset of V, some sub-vertices. Note that I don't need to take all vertices. I can take just 3 out of 6, for example. I don't need to take all edges. I can take whatever, just a few of them. So here's another subgraph. Let me just draw it. I could have taken 1, 5, and 3 and say only those 2 guys. It's also a subgraph. Let me call it H prime. Right? So you can really take everything. Just grab your object, mark a few, exactly like I did it here, mark a few vertices, mark a few edges, and whatever you get is a subgraph. And there's one extra notion we need. It's kind of, well, everything here, everything that lives inside here is a subgraph, but maybe there's a more kind of the extreme subgraph. So if I just pick a certain number of vertices and put all edges, it's called the full subgraph. I'll have in a second another example for you. Okay, so let me pull up the example. And I hope that makes sense. A subgraph is just I mark some of the vertices and some of the edges and call that a subgraph. I don't need to necessarily draw it next to it. I hope that makes some sense. So I have my parent graph here, and a subgraph is essentially anything. I mark some vertices, I mark some edges, and here's my subgraph. But this subgraph is not full because, for example, this edge, it goes from here to here. Yeah, this edge that goes from here to here is not in my graph. And in the full subgraph, you include all edges that you possibly can include. So on the right-hand side, there is the full subgraph on those 4 vertices, and all possible edges are included. Right? The only edges that are not included are the ones that go to the vertex which I decided not to include in my subgraph. And then if you step back for a second, that makes kind of sense. We are studying those structures, and we're studying those structures essentially up to connectivity. It really matters which one is connected to which. What should be a substructure? Well, you just pick a few of the vertices and you pick a few of the edges. Yeah? So you could focus on, so you have the graph associated to Facebook, and you could pick out a subgraph corresponding to maybe a certain type of people that would correspond to taking out certain vertices, and then maybe their connections, which would be exactly picking out the edges. Right? It's a substructure of what we are studying anyway. Hope that makes some sense. Again, difference between a general subgraph and the one and only full subgraph. There's only one of them if you just fix the vertices, because you just take all possible edges. Okay, I hope that makes some sense. And I just wrote it down again here. So what are my edges that I took? Well, I took 1, 3. This one is here. 1, 3. I took 3, 5. This guy, and maybe greenish 5, 1, which is this guy. Right? And I have W up here. So W is, of course, just 1, 3, 5. Right? Those are the vertices that I pick out. 1, 3, and 5. Okay, hope that makes some sense. And immediately some question arises. So let me mark the graph again here. So I have it on the other side, but let me put it in again. So we have this little graph here. And it looks like one of the ones we have seen before. So we had those cyclic graphs. They're just really, well, circles. And it looks like the cyclic graph on 3 vertices, but there's some problem. So let's go back to the cyclic graphs. Maybe we can see the problem. Here's a cyclic graph. And it really looks like this guy, right? The third one, but the difference is this one is 1, 2, 3. And the other one is kind of stupidly relabeled. Where are we? Is 1, 3, 5. So strictly speaking, they're not the same. If you just write down the set, this one has 1, 3, 3, 5, 5, 1. And the other one has 1, 2, 2, 3, and 3, 1. Right? They're not the same set. But obviously, they are the same. So eventually, at one point when you're studying structures, and we are studying graphs right now, we need to kind of decide what equality is in our case. And I think I want this graph to be the other one. I really don't care about the labels. I say again why we want this. Because we only care essentially about the intrinsic properties of the object. So this has 3 connections and they go around in a circle. The other one, let me just draw it next to it, has 3 connections as well, and they just go around in a circle. And there's this stupid 1, 2, 3, and this is just stupid relabeling issue. And I will now explain how to get rid of this issue, and then we get the real class of graphs we really want to study. Right now, I said again, we kind of have the problem that we like to study those objects up to their intrinsic properties, but they kind of depend on the choice of labels, for example, and that's kind of not good. Whether you call this 1, 2, 3, 1, 3, 5, or whatever, Apple, train, and bus, doesn't really matter, right? It's still the same graph. Okay, so let's get rid of this ambiguity. Hope that makes some sense. So we have now the setting of graphs, but we are somewhat not quite doing what I promised you to do. We still need to kind of identify graphs, because right now we're just writing them down as sets. And as a set, maybe I just do this, as a set, the set 1 is not equal to the set 2. But somehow, of course, they just have both one element. So we will somehow identify them. This is just a relabeling question. Right? So what does it mean for 2 graphs to be the same? That's exactly the question I would like to address now. So 2 graphs are isomorphic. That's a notion we will use. They're isomorphic, and we write this symbol which you might have seen before. It's kind of a little bit overused in mathematics, but anyway. So G is isomorphic to an equal sign with a twiddle on top. Well, you can read it, but let me explain what's going on. Okay, I just told you that we kind of have this relabeling problem. We have a set 1, 2, 3 for one of the graphs, and we have a set 1, 3, 5 for the other graph. And these sets are kind of the same, but they're still not the same. They have different elements. So what we do, how can we identify those sets? We say that there's a bijection between them, which we call F. So this is V and this is W in the example above. And it really just does something. For example, you could send 1 to 1, 2 to 3, and 3 to 5, the other way around. 3 to 5. And bijection just means it's a 1-to-1 matching. For everything here, I have something here. For everything here, I have something here. I have exactly one thing on the right-hand side. And this is, what is this doing? This is relabeling our system. Whether I put 1, 2, 3 here, or Apple, train, and bus, doesn't make a difference because this is now my relabeling. 1 goes to whatever Apple, 2 goes to train, 3 goes to bus. Okay, so that's kind of relabeling our vertices. I kind of don't care how you call them. Remember that this is kind of a choice. I just decided to call my vertices 1, 3, 5, but maybe you would have decided to call them something different. And this is not good. We kind of should have the same, we kind of should agree what it is we're talking about. So how can we do this? Because everyone will come up with their own solution. Well, we just say the only thing that matters is the number of elements, and we have some matching between them. Okay. So this is what I'm saying here. But we need one more property. So this is not quite okay, because this would, for example, we're not quite done. This would, for example, identify this graph with just 1, 2, 3, and no edges at all. It would identify it with, what is a good color, with our cycle graph, with 1, 3, 5, because we would just say, okay, this vertex goes to this vertex goes to this vertex goes to this vertex, and that's a perfect matching. But that's not what we want. I mean, I don't want to identify the right-hand side, the left one with the right-hand one. One of them has no edges at all, so I clearly shouldn't do that. And what I say, additionally, is that my map satisfies the property that connectivity is preserved. So if there is an edge between V and V prime, to begin with, there should be an edge between the image of V and the image of V prime, which exactly avoids this problem here. It sends edges to edges, but now I have no edges where I could send them to. Yeah? So if is an edge, then there is an edge. That's the whole point. And we call this, we have an isomorphism. And isomorphism preserves connectivity. This is exactly what we want, because we want to study those graphs up to connectivity. Right? And we'll just get rid of the stupid relabeling nonsense. Right? I say it again, whether you call your edges as your vertices 1, 2, 3, 4, 5, 6, or you come up with some really fancy thing, whatever, doesn't matter. We can just relabel it, and everyone is happy. Just keep in mind, and that's a really crucial property, that edges need to go to edges. So connectivity needs to be preserved. Otherwise, we collapse graphs, we identify graphs that we don't want to identify. Okay, let's pull up some examples. This one is fun, so remember, let me try to draw them. Remember that this one was just, we have a certain number of vertices at the bottom and at the top, and we connect everything at the bottom with everything at the top. And I just told you that one of them is bottom and one of them is top. And all I'm saying is that they're isomorphic to just turning your head and just drawing it the other way around, which absolutely makes sense, because that's what we actually want to do. So there you go. Of course, this is the same. You just send all the top vertices to the bottom, all the bottom vertices to the top, and it turns the picture around. Right? So my morphism here, my isomorphism would take those three and send them here, and would take, what is a good color, maybe light blue, those three, and send them here. Yeah, and our little friend here, this one is now isomorphic to so this one, which was really just, let me draw it again, which is really just this guy here again. It looks exactly the same. It has different labels, 1, 2, 3, and the isomorphism is sending 1 to 1, oh, I do it the other way around on the slides. I send 1 to 1. No, sorry, it was right. So I send 1 to 1, 3 to 2, and 5 to 3. And the point is, let's double check, this edge, where does it go? It goes right here. So connectivity here is preserved, and you would need to check that for all edges. But in this case, it's quite clear, right? This edge goes, and this edge goes here. Okay, so this is kind of the right notion. We want to study graphs up to isomorphism, because this isomorphism is really a kind of a labeling problem. So here are a few more isomorphic graphs. Okay. These are all the same graphs. So the top one is just a different way of arranging the other ones. And you can always write down an isomorphism that matches everything, and being careful that edges go to edges. Right? The only thing I did is that the edge in the middle is now slightly placed here on the outside, for example. A little bit more difficult to see is that this one is the same as the top one, and the other one is the same as the top one as well, up to isomorphism. I hope that makes some sense. And why are those complete graphs so important? So let me go back to the complete graphs. Last time I kind of pulled them up. I had this list of, too many slides. I had this list of graphs, right? So we had the cycles, the lines, and then we had those complete graphs. And I said, yeah, maybe that's not quite the first thing you would write down, but here comes the reason why this is a really natural family to study. So complete graph was really just be as generous as possible. Just put every possible edge, right? So just complete, it's complete, just put every possible edge. And here's an a priori reason why complete graphs are fantastic, if I can find it. Okay? So suppose you have one of those nice graphs, and let's ignore duplicate edges and loops, then there will always be subgraphs of a complete graph. It's kind of the structure, the complete graph is a structure that contains all the others as a substructure. So we certainly should study those complete graphs. And we already saw an example. So here, this graph was a subgraph of, maybe I just write it like this, a subgraph of a complete graph. So this is a complete graph on 6 vertices. And this is true in general. You will find everything somewhere in some complete graph. Which kind of gives I think, a nice justification why you would study this family, which looks a bit strange if you see it for the first time. But they contain everything, so we clearly should somewhat study them. Okay. Can we see how the proof goes? Well, so how can we find, so given a graph, how can we find a complete graph such that our graph sits inside? Okay. The only thing I do is, it kind of makes sense. So let's have a look at the graph again here. Okay. So first of all, you want to have enough vertices. And I'm not saying that one complete graph contains all other graphs. I'm saying for every graph, you will find some complete graph such that your graph sits inside. And that's what I need to say, because if I have a graph with 12 vertices, I clearly can't find it in here, because this guy has only 6 vertices. So what do? Okay. So I start with my graph. I label my vertices 1 up to n, or v1 up to vn if you want. And this tells me that it probably sits in kn itself. Okay? So let's have a look. I could make this graph a subgraph of a much smaller graph if I only need 3 vertices. And everything with 6 vertices should sit inside here. So let's try to do that. Okay. So with v1 up to vn, that's from our original graph G. Here's our little g. And here's our little vertex set of kn, which I just call 1 to n. And the edges were what the edges were. And we can now define a subgraph, which is isomorphic to our given graph. And I will draw a picture in a second how we do this. But essentially, it should send v1 to 1, v2 to 2, vn to n. Okay, so it does this. and so on. Let's draw a little picture. So let's say we have 4 vertices. Here's a complete graph on 4 vertices. Just draw 4 vertices and I connect everything. Flop, flop. Okay, and then now I have a graph with 4 vertices that comes up somewhere. Whatever, something random, something like this, for example. And I claim it's a subgraph of the bottom one. So what do? Okay, I label my vertices. So this is 1, 2, 3, and 4. This is V1, V2, V3, V4. And now what I do is I send the top one to the bottom by drawing it in. So I take this vertex, this vertex, this vertex, and this vertex. I take this edge, this edge, this edge, and that's what's my graph H. And the graph G is sent perfectly to H. That's all I'm saying on this side here. Right? I construct my set H by just looking at the image of my vertices and just put them in there. And by construction, this is an isomorphism. Why? Well, I've sent my vertices to copies down there, right? Just 1 to V1, I just relabel them. But also my edges perfectly match, go to the edges down there. So it's an isomorphism. And what you can do in general, you just write down an arbitrary graph, you write down your complete graph with the same number of vertices, and just mark the corresponding vertices and edges in the graph. And I think that's pretty cool. So it kind of gives a justification, as I said again, why we would like to study those complete graphs. Well, it makes sense, right? They contain every problem, essentially, that we could come up with. So we definitely should write them down as an own family and should have a look at them. And they will appear everywhere because, as I just said, they contain every problem in some sense. I hope that's reasonably clear. Okay, so let us summarize what we have done so far. So essentially, we do another step now. We do something new. So essentially, what I told you is I told the story about substructures in our graphs, because graphs are our structures, and we should study substructures, which are subgraphs. And a subgraph is essentially just really, let me pull up the picture again, really just this. I have an original graph, I mark some things, and I call that a subgraph. It's kind of, I think this is obviously what a substructure should be. You might disagree, but this is what people call a substructure in graphs, right? You just mark some things and some edges. And I also told you that everything can be found in the complete graph, which kind of justifies why we want to study them. Okay. I hope up to this point the story is smooth and beautiful. And now it gets even better. Topology just gets better. So let me remind you what I pulled up at the very beginning. Here was my picture of how people use graphs to kind of model the brain. And it clearly matters in this picture, and you can see a brain here, right? So it clearly matters how the graph arranges itself in space in this case. So we want to study this property. That's what I'm going to do now. I'll tell you a little bit more. So now we are not thinking about an abstract graph, but now we want to think of it as kind of realized somewhere in space. And the formal notion of how that works is called a planar graph. Right? I'm not doing space right now. We're doing space in a second. We're doing the plane. So in R2, really just my slide here in front of you. And I will put them in the plane. So I call a graph planar if I can draw it without intersecting edges. I will have several examples for you. And the drawing, I call the drawing itself a planar embedding. It's just a terminology. So let me repeat terminology. Terminology is always a bit annoying, and people get confused. Planar, like plane, I can put it in the plane. I can draw it in the plane, and the drawing itself is called a planar embedding. Very good. Okay, let's have a look at this example. And now it gets a bit tricky. So people get that wrong. So let me just repeat it several times. The graph itself is the abstract object. Remember, we study things up to intrinsic properties. The planar embedding is a drawing of that graph such that no edges intersect. So I can have a graph. These graphs are the same. I just have redrawn the edge here. I just do this. I take this graph, I pull this edge outside, and it looks like this. Right? That's the only thing I've done. So they're the same graphs, but they are different drawings of the graph. And this one is planar, this one is not. But the graph itself, because it has one drawing that is planar, is planar. So this is always tricky, and we will definitely ask those questions. Is the graph planar? And I will show you a picture. And you're supposed to look at the picture and tell whether the graph is planar. But it's not enough to say, oh, the picture is not planar, because there could be a drawing of the graph that is planar. I hope that makes some sense. Abstractly, they're the same, but drawn in the plane, they are not. And I'm interested in those guys. Okay. So if I ask, is this abstract graph planar? The answer is yes, because you could draw it like this. Okay, and there are two more planar graphs. So every path graph is planar. You just draw it as a line. You don't need to do that, right? Do it for this one as well. You could, if you want, draw the path graph like this. Still the same graph, just completely weirdly rearranged. Right? Say it again. That's a property of a graph. A graph can be planar, and you can check that by drawing a planar model, by drawing it in the plane. Similarly, the cycle, you don't need to draw it nicely. You could draw it with self-intersections. You could do something like this if you're really sophisticated. And that's not a planar drawing, but the bottom one is a planar drawing. So let me just pull up again the picture we had before, just to make it clear. These are all the same graphs, but only the bottom ones are planar drawings. The top one has intersecting edges. They're all the same graphs, but the drawings are different. And that's what we want to do, because we somehow need to study graphs not just as abstract objects, but in this case, we want to study them, how they live in the plane. So I'm interested in the bottom ones, but the whole set, everything you see here is one graph. And I'm asking the question, is it planar? And the answer is yes, because I could draw this picture, I could draw this picture, or maybe this one is the easiest one. I could draw this type of picture. I hope that makes some sense. And it's somewhat not easy to decide whether a graph is planar. And I will postpone that problem for a while. So we will answer it. But for now, it's just, if you have some graph, and it looks a little bit crazy, how can you ever decide whether it's planar? So let me pull up the complete graph again. Okay, so let's look at this one. I mean, this is not a planar drawing, as you can see. It has intersecting edges. But maybe there is a way to draw it in a planar way. Not so easy to see. The point is, if you have a planar drawing, if you can draw it in the plane, then you can immediately decide, oh yeah, that one is planar. If you see this picture, we somehow need a better method to decide. Because maybe I could pull this edge somewhere else, and then I could pull this edge away, and maybe they don't intersect anymore, or something like this. Not so clear. We will answer that question, but it takes a while to answer it. So for now, we kind of can't really answer it. Right? So deciding whether a graph is planar, if I give you this picture and I ask the question, is it planar? You somehow need to decide, is it or not? Okay, if you find a drawing, you're good. But what happens if you don't find a drawing that is planar? You somehow want to decide a priori that, oh no, this can't be planar. Right? That's kind of a task I'm bringing up right now, and we really need to answer that eventually. For now, we can't really answer it. Okay. It's pretty easy to see that those graphs are planar. Okay, why are the first three planar? Well, I showed you a planar drawing. There are no intersecting edges, so they get a little check. They get a little check. These are kind of clear. And here's this friend. And I give it a check, but it's not obvious, because I show you a drawing here with an intersecting edge. You have this little problem here in the middle. But I could draw it as follows. Just take the same thing, put the edges here, put this one here, take the middle one and pull it outwards. So I just take the middle one and pull it outwards. So I've found a planar drawing of K4, so this one is actually planar as well.
Sorry.
Yeah?
I mean, what if this one can be under and this one can be over? I mean, for graph, do we need to consider about the under and graph relationship?
No, this is in the plane. They just intersect. No strand goes over or under.
We just
In the plane, exactly. They can't go over or under. They either intersect or not. It's like a street. It intersects or not. We're not building bridges or tunnels yet. Not yet. Okay. These ones are planar, and we just proved that essentially by drawing it. That's really nice. So we can prove things by drawing it. Okay. So draw pictures, and the pictures will prove whatever kind of theorems, propositions. This one is not planar. And I can't tell you why right now. We'll see that later. But for now, the only thing we can do is we can try to pull edges around. So let me try to convince ourselves this can't work. But this is kind of not getting us anywhere because there could be some crazy drawing that doesn't work. So as you can see, there are some problems in the middle. So maybe if I pull out the edge, the top edge here, if I pull it out, okay, fine, then it already looks a bit better. Maybe I can pull out one more edge, okay, so maybe I can just pull out the next edge as well. But now I have kind of a problem because if I would like to pull out this edge here, right? I would like to pull it out, but if I pull it out, it somehow intersects here again. And you can kind of try to play around with it a little bit, trying to pull out edges to various positions, and you will kind of realize that whenever you kind of resolve the crossing, the intersection here in the middle, you will create another intersection somewhere else. You somehow can't draw a planar model, but it's not really a proof. It's just saying that I can't do it, which is not really a general proof, because there could be someone really smart and just draws a planar embedding for you, it's just out of magic, and it could work. So we need some argument to decide that this one is not planar. I just tell you right now it's not. Okay, I just tell you this one is not planar. Okay, so here, believe me, it's not. We'll see later an argument why. But then it follows that all others, all bigger ones, are not planar either, right? From K5 onwards. Why? Because K5 sits in K6. So if K6 would be planar, I could draw it somewhere. I would put in K5 in a second. I could draw it somewhere without crossings. I would be able to draw that one as well. K5 sits in K6. K6 sits in K7. K7 sits in K8, and so on. So K5 is just these guys here. That's the collection of those vertices. If you arrange them a little bit, you will see it's K5. So if I could draw K6 in the plane, I could draw K5 as well. So as soon as we know that one of them is not planar, all the others are not. And that's a proof. But just for K5, we can't do anything right now. Some problems in life are a bit more difficult, so I postpone it. My favorite strategy, just if you run into troubles, just postpone it until you can't postpone it anymore. That always works very well, highly recommended. So we are doing exactly that. I showed you a really good notion, planar graphs, which is really kind of important because we want to think of them as living in the plane. But I don't really tell you a way to decide it, which is a bit shit. But I kind of need to postpone that problem for a later lecture. Okay, and you wonder, why are we studying planar graphs? What about free space? So what about, well, our little lecture hall here? So maybe we should draw graphs in free space, and turns out that you can always do that. So for planar versus non-planar, in the plane, there's a problem. Some graphs can be drawn, some graphs can't be drawn. But as soon as you go into free space or higher space, we can all draw them. So you can put everything without crossings into free space. And there's a really, really beautiful proof that I'm going to show you. But first of all, let's just digest it. So we had this problem in 2 space, and I called that planar. Right, here's R2. And I rambled a long time about that this is really difficult and I will postpone an answer and whatever. And then I go one dimension higher. I go into 3 space. So I draw it now I draw it in the lecture hall. Let's say I would be able to do that. And it turns out that I can always do it. Okay? So it's kind of fun. So in 2 dimensions, it's difficult and interesting, whatever. Difficult or interesting, it depends a bit on your perspective. And in 3 space, it's easy. And I show you how that goes. And it's really a beautiful proof. And it's one of these proofs that if you've seen it for the first time, you will somehow never forget how it works because it's just really amazing. So just standing here and trying to prove that theorem, it is not quite clear to me how I would do this. Right? So how would I do this? I have an arbitrary graph. So how could I ever attempt to put it in 3 space? And this is how it goes. It's extremely beautiful. Okay, I do the following. I put it on the book. Okay, what do I mean? Okay, I have a book here, and my book has only 3 pages. But in general, I might have more pages. I have some book with a certain number of pages. And along my binding of the book, I put all the vertices. So maybe let's get rid of the colors again. So I put all the vertices of my graph. I take some graph. So this is K5. I took K5 as an example here. You take some graph, and you put all the vertices along the binding of the book. And then you still have all the pages to play around with. And you just put edges on pages. You could put one edge per page if you want, if you have enough pages, because there's enough space. So, and then they're just far away, because they're on different pages. And that's it. So you can draw it in 3 space. I say it again, because it's absolutely fantastic. So this is actually not exactly what I did, but you put them, you think of it having a book with a lot of pages, as many pages as edges, for example. You put all the vertices on the binding, and on each page, which just goes out into 3 space, you put 1 edge, for example. And then they won't cross because they're on different pages. And that shows you that, that's it, that things live on a book. Turns out that you can do a little bit better, but essentially that's it. You have a book, and now you have all this freeness of having multiple pages, and you can just put the edges on the various pages. And why am I telling you this? Because really, and we will see the same problem turning up, or the same type of structure turning up in later lectures, graphs are low-dimensional objects. So eventually there should be enough space to put them into, and somehow it turns out that 3 space is big enough to put every graph inside, because they're 1-dimensional objects. 2 space is kind of in between, and you clearly can't draw most graphs in 1 dimension. I mean, I can draw this one in 1 dimension, but this one is already something I can't draw in 1 dimension anymore. So kind of 1 dimension is clearly too small to draw them. They're just 1-dimensional themselves. 2 dimensions is kind of the interesting case, and 3 dimensions has enough space to put them into. And I think that's pretty cool, actually. Okay, and that's why we are mostly studying planar graphs, because that's the interesting case. So this one doesn't even have a name, because just everything satisfies this property. I hope that makes some sense. Okay, let me just pull up a real-world problem why we would like to do this. So what is this whole notion about? Well, you could think of the following. So this is usually the story people tell. So we have a graph. So you have a certain number of houses, and you have, well, a certain number of facilities like water, gas, and electricity. And you kind of want to connect them to all the houses. And let's say our world is a plane. So you need to do this without ever crossing. And it turns out that for this example, where you have 3 facilities like electricity, gas, and water, and 3 houses, you already can't do this. So what is the problem? Well, you could clearly, so I connected everything here to the 2 rightmost houses, and we can clearly still connect this one here, connect this one here, but this one is stuck, as you can see. It's somehow completely in between red, so we can't pull it out. And the graph you see, I will draw the graph in a second, is actually not planar. And this is kind of a problem if you want to design like those connecting of houses to various facilities, because eventually you need to really have a little bridge or a little tunnel, because you really just can't do it in general. So let me draw the graph. It is our friend, so here are the houses, and here are the facilities. Is our friend K33. So what we want to do is we want to connect everything at the bottom with everything at the top. So let's try, and let's just do it the naive way. Whoop, whoop, whoop. And we want to do it in a way that no edges cross. And this is another example of a graph that is actually not planar, which, let me pull up the picture again, somehow really makes, has some real world applications, because you can really just think of it as connecting certain things with connecting certain things, and you just can't do it in general. So you need to eventually build a bridge or a little tunnel. And that's where this problem of planarity comes from. And we can also think of it as being a street planar. Eventually, you probably need a bridge because you just can't connect streets anymore, or a tunnel. And that's why you see bridges and tunnels in the real world, actually. OK, I have one more topic. It will only take 5 minutes, and then I let you go. So let me just summarize what we have done in this second part. So in the second part, I just said, OK, we now want to study. Remember, my story is we have this toy model of the world, which I call graph theory, and we want to study as many properties in our toy model as possible. And the property I focused on in this case is, can we put them in space such that no edges intersect? And we ended up with this notion of planarity in 2 space. That's an interesting question. And my little book picture shows here that in 3 space, the question is not interesting anymore. So we won't look at this question in 3 space. But you somehow need to come back to planarity, because I kind of promised you, well, I gave you a problem, essentially, or something you would like to study, but I don't give you a solution, which is kind of a shit way of doing it. But we still need to postpone it until a little bit later. OK, so one more, and then like in 5 minutes. OK. A little statistic I would like to use for a graph is just the degree of the vertex. Right? For a graph, connectivity counts, and the degree of the vertex is just a number that is associated to a vertex to look at how many neighbors it has. It's just the number of edges that you see on with endpoints on your little vertex. So here we have 3, because I have 3 loops. Here we have 5. So 1, 2, 3, 4, 5. And the degree of 4 is 2 here, for example, 1, 2. And turns out the degree of the vertex is very important. It kind of makes sense, right? It's kind of, instead of studying the graph itself, you have a bunch of numbers now associated to the graph for each vertex. You could write down its degree. It's a little bit of less information, but it's somehow also easier to handle, because you just have a bunch of numbers associated to your vertices. Hope that makes some sense. Here are a few more examples. The degree of 4 is 2. 1, 2. The degree of 4 is 5. Ooh, let's see. 1, 2, 3, 4, 5. And the degree of 4 is 5. Yep. So if you just go along this little circle here, you'll see 5 edges coming out of 4. It's actually not so difficult, right? You could just decide for every graph what the degrees are. And I just pull it up and we prove it next time. There's a really fun equation which says that the sum of the degrees is always an even number, and then it's not just a random even number, it's twice the number of edges. So we'll do that next time, but let's just double check that. So what is the number of edges here? 1, 2, 3, 4, 5, 6. It has 6 edges, so twice the number of edges would be 12. What is the degree of every vertex? The degree of every vertex is 2, and we have 6 of them, and 2 times 6 is 12. Okay? And you can do that in absolutely any graph, which gives us the first really nice formula. This kind of comes out a little bit surprisingly, a local information and a global information. Right? The vertex degree is the local information that you can read off locally at a vertex, and the number of edges is clearly a global information of your graph. Anyway, thank you so much for coming, and I hope to see you tomorrow.